chapter 10, we've been working on counting strategies, ways we do counting of different kinds of events happening, right? And we'd looked at, in section 1, making lists. And lists work. They work fine as long as the lists don't get too long and overwhelming. And then we're like, this is ridiculous. I want to keep making the list, right? And then section 2, we learned about the fundamental counting principle, where we looked at different ways of counting different strategies of things. And we kind of pushed back into section 10.1 and said, hey, we could have answered these questions of just how many of these happen if we use some of these other strategies. All good. Okay, so 10.3, we're going to continue that discussion, and we're going to be taking a look at permutations and combinations. And as we take a look at this, this is going to be, again, another way of doing some counting. And it's going to look a little bit like some of the things we were doing in 10.2, where we had factorials. Nod your head if you remember factorials. They're those exclamation points. Okay, so we'll review that just a little bit as we get into it, and it will show up heavily in our classwork today. So our leading idea is the following. Permutations and combinations help us explore the different ways things can be arranged or selected, highlighting the vast possibilities that arise from a limited set of elements. In a similar way, faith in God acknowledges the many paths and choices life presents, trusting that amidst this complexity, there is a purposeful design. Just as we use permutations and combinations to make sense of variety and order, God gives us meaning and guidance through diverse experiences and opportunities. So I'm in a Bible study. We're looking at the book of Daniel right now. And one of the interesting things that's happening at this point in the book of Daniel is that very clearly God shows King Nebuchadnezzar, if you know the story at all, future events. He shows him exactly what's about to happen. And the very interesting and cool thing about that is Nebuchadnezzar is not a believer. He's not Jewish. He's got nothing to do with God. And he does a lot of really crappy stuff, honestly. I mean, really, he's terrible. And the very cool thing that we've been discussing is how God is still in control over all of that crap. I mean, really, like he's still the one that's in control of that. One of our ladies in our study has said, God is he's in control, but he's not a dictator. And he's that for you too. He's in control. He's got a plan, but he's not going to make you do what he wants you to do. You get to make that choice. Let's pray. Dear Heavenly Father, I thank you so much for an opportunity to take a look at different strategies for mathematics and the ways that it can push into our personal lives, into our spiritual lives, and direct and help us direct our thinking back toward you. I pray that as we work today, that the mathematical operations and the details would not get in the way of the overarching themes of order and structure that are present in everything we do in this section and in this class. We pray these things in Jesus' name. Amen. So permutations is the first thing on the agenda. Permutations is a number of arrangements. So specifically, it's a number of arrangements of, and then they're using some letters here, right? Some arbitrariness to it. In things taken R at a time. So jot down this formula. The N and the R kind of look like subscripts surrounding the P. P stands for permutation. The N at the beginning is the total number of things you're selecting from. Okay? So if we were going to create something of this classroom and you were all in the pool of people to be selected, that'd be counting the number of people in this classroom, that'd be the number at the beginning. Then R at the end is how many from those you choose. Right? So you go to the caf today and you've got all these choices of foods to eat, and you're not going to eat them all. You'd be sick. You're going to choose a specific number of them. So that second number is how many you're actually choosing from the choices you have. And we see the formula showing up with those factorials that we mentioned last time, right? So the value on top is all the ways that we could choose things. It's all the choices we have. It's in factorial, okay? And then on bottom, what happens is we see n minus r. What is n minus r? Well, if this r here is the number we choose, what would n minus r be? It's the number we don't choose. Right? It's all the things in the caf that you did not choose to eat if you counted them, right? So these are the number that are not chosen. Hang on, let me write it differently like that. Just say number not chosen. Okay, it's the amount of things that you are choosing not to take part in. So if we were collecting the number of people in this classroom, it's the number of people that didn't get picked to be on the team, right? Or be on the committee or be on the whatever. It's the number of unchosen elements. The really important thing to remember when we're working with permutations, in comparison to combinations, which we'll do in a little bit, is that the order matters in a permutation. So do you remember when we were doing examples of where we were creating a group of students and there was a president and there was a treasurer? Do y'all remember that? And when we did that, we said that it was a different order, if the president was this person or if the treasurer was that same person, right? It was, even though the letters just sort of flipped, it was a different ordering of what was happening because they had different responsibilities. That's a permutation concept. The order of something matters in a permutation, okay? So we'll see another example here in a second. Let me show you the other one that we're working at primarily in this section, which is combinations. Combinations, the formula looks very similar. It's the number of subsets of n things taken r at a time. N is still the same, the number you're selecting from. The r is still the same, the number you're selecting. Okay? But what do you notice about this formula that's slightly different than the last one? Yeah, there's an r factorial additionally in the denominator, right? That wasn't there. So this first piece, same as before, is the number not chosen. And this piece right here is the number that are chosen. And this actually is a better description probably of what happens when you go to the CAF. It doesn't matter if you pick the pizza and put it on your plate first or last, it still went on your plate to be part of your lunch. It doesn't matter the order it was picked in, okay? That's a combination, and you see at the bottom it tells you the order does not matter. Do you have a question, David?
Yeah, how would you write that out in a number?
We'll do one. I promise you're going to see that and how it looks. Absolutely. It's a good question. We saw this happen as well in section 1, and then we revisited in section 2 when we looked at creating a committee. So if you remember back to a week ago, and we created this committee of 2 people, and we talked about the fact that we had to divide by 2 to remove the double counts. Nod your head if that sounds something familiar, right? It didn't matter whether they were listed first or second. If they're just in the committee, they're just a part of the group, it's the same group. That's a combination. The ordering of something not mattering creates a combination. And the context itself will tell you, you have to think about it. It's not going to just say, use a combination to do this. It's not going to say that. The context is what we have to interpret to decide which of these we have going on. So the first thing I'd like for us to do is just practice kind of what David asked for, is what does this look like in numbers? Because that's actually the first part we're going to look at. So we're going to compare what happens with the 12P3 and the 12C3 in terms of the formulas and how they work out. And you'll see the connection back to what we did in 10.2, because we did things like this in 10.2, okay? So the formula says that I put the first number on top, 12 factorial. It's all the choices that are at my disposal. There's 12 items that I have to pick from. And on the bottom of a permutation, what I need is 12 minus 3. I need to know how many are not picked. So feel free to just write it as 9 if you want, but it's coming from 12 minus 3. How many choices did I not actually choose? Okay, well, 9. I chose 3. I didn't choose 9. Okay, so this number right here is the number I choose. This number right here ends up being the number that are not chosen. Okay? So this particular number set could be applied. This is what happens when we start talking about Bible stuff. How many disciples were there? There were 12. And there are 3 disciples that are in Jesus' inner group. Do you remember who they are? Peter, James, and John. Those are the 3. Peter, James, and John. Right? And there kind of was an ordering of them too. Right? So John says he's the disciple whom Jesus loves, so he probably puts himself at the top of the list, right? Peter's the rock on which Jesus builds the church. I'm not really sure, but James gets included. It's got to feel special. It's important, right? He's not the other people who didn't get included. Anyway, so there's 9 that got left behind, right? There's 9 that didn't get taken. When Jesus goes up to the Garden of Gethsemane, he takes those 3 disciples with him further in to pray. There's 9 that get left behind. This is the 9. They're the 9 that are not chosen. Okay? In terms of calculation, though, what does this look like? This is what we did last time. We actually wrote down that this is 12 times 11 times 10 times 9, and we could keep writing after that 8, 7, 6, 5, 4, 3, 2, 1, right? But what we learned last time is that there's a shortcut to doing that as well. Because I could actually write this as 9 factorial and stop, I'm allowed to do so because it will match exactly the 9 factorial on bottom. So if you want to write down 9, 8, 7, 6, 5, 4, 3, 2, 1, you can do so, but you're going to write it on top and on bottom, and then they're all going to cancel out anyway. So I'm going to stop at this first opportunity to do so, which is the 9 factorial. And what I end up with then is 12 times 11 times 10. So what is 12 times 11 times 10? Somebody said it. I thought. No, I just imagined it. 1320. Thank you, Micah. 1320. Okay? So there's 1,320 ways that we could choose 3 things when there's 12 to pick from. If the order matters, right? It mattered the ordering of those choices for whatever reason. Okay? Context aside, we'll talk about that in a moment. If we do a combination, the setup looks quite similar. We have 12 factorial on top. We have 12 minus 3 on bottom. But we also have 3 factorial on bottom. So in some sense, right, like really this is truly what's happening, what we have on bottom is the number of things we don't choose. Well, that was 9 of them. And the number of things we do choose, that's 3 of them. How many we choose and how many we don't choose goes into the denominator of a combination. And we can write them out much like we did before, 12, 11, 10, and I'm going to stop at 9 factorial. It matches the 9 factorial on bottom. And I'm going to write down the other one, which is 3, 2, and 1. And the 9 factorials, still cancel. And you can do this one of 2 ways, which we talked about last time too. You can multiply across the top. In fact, we know what it is. It's 1320. And then you could just divide it by 6. Right? Your calculator do that just fine. Nothing wrong with that. But it's also correct, and when we get to longer expressions, more helpful, to recognize that every piece of the denominator will reduce with something in the numerator. And we saw that in practice last time too. So we did things that looked like this. Hey, 3 and 2 multiplied make 6. 6 divides 12 and leaves me with 2 left over. We did that, right? So we could, instead of multiplying 12, 11, 10, and then dividing it by 6, we could end up just multiplying 2, 11, and 10 to get our answer. And what is 2 times 11 times 10? 220. So it should make sense that if the order matters, there are more ways that these things can turn out. And if the order doesn't matter, that's the combination, there are fewer ways that things can turn out. Yes? The 12 on top by the 6 on bottom, exactly. Okay, so much of this should feel like we did that last time. The only part of this that's new is the original setup where we put the numbers in. Okay, is that all right so far? Okay, so what we need to be able to do is to look at a problem then and to decide which of these scenarios am I in. In fact, does the order matter or does it not? And we're going to also look at some language that shows up, like some details in the way that the wording is formed that will help us to clue into that too, if the context is maybe something that's not as familiar to us. This first one is one of those where the context may not be very familiar to you, okay? So this is straight out of a My Math Lab resource. I didn't make this up. So I wanted you to see something that feels very much like the way they word questions. That's why I chose it. Jeff Hubbard, a contractor, builds homes of 8 different models and presently has 5 lots to build on. In how many different ways can he arrange the homes on these lots so that 5 different models will be built? So, as we take a look at this, you may look at this and say, I don't know anything about building homes on properties. This context does not resonate with me. I don't have the prior knowledge, this wording of this is not making sense. Okay, that's a legit thing that could happen. Yes, David?
I think I know how to say that.
You think you know how to set it up. Okay, so let's go to that. Which one do you think it is? Because that's what we have to decide, right? We have to decide, is it a combination or is it a permutation? So before you decide, I want everybody to think for a second, which one do you think it is? And if you're wrong, it's okay. We're going to talk about that. Which one do you think it is? Okay.
Permutation.
So you think it's a permutation. Does anybody agree with Jordan that's a permutation? Got a few hands. Okay, seems like a permutation to some of you. Does anybody think, no, I think this is probably a combination? Anyone in that park? Nobody's nodding their heads. A few people. Okay, here we go. So now we have to decide which one it is. So let's actually take a look at some language-specific things that can help clue us in when the context maybe isn't something that resonates with us. Sometimes context is going to be very obvious. You're going to be like, well, obviously. But this one's context is a little bit shadowed, right? If you don't have a good feel for the context, it might not actually work for you. So right here, this word arrange, or this phrase, let me say arrange the homes, is actually very key to making this decision. If you're arranging them and not just selecting them, that means order matters. Okay, it's the arrangement of something. Imagine if you're in your room and you're arranging things on a bookshelf. Or if you're looking at your phone and you're arranging apps on your display. I will tell you what, anytime I pick up one of my children's phones, I can't find anything. Because their screen doesn't look like mine. Theirs is not arranged the same way. It confuses my brain, right? The arrangement on the screen matters. It looks different. So when we're talking about an arrangement, we're talking about order mattering. Does that make sense? That's one of those key phrases. This right here tells us that the order matters. And when the order matters, which one am I working with? That's a permutation. So this is going to be a permutation. Okay, is everybody okay with that part so far? Fabulous. So I need to figure out what number is there. I know I've got a P here, right? It's a permutation. How many things am I selecting from? 8. There are 8 different house models. And it says he's going to choose different models. Like he's not going to choose like the same model that he builds all of them the same, right? Like that matters. That's inherent in the way that the problem is also described. But how many is he going to choose? How many of these different blueprints, essentially? 5. He's going to pick 5 of them. Okay, so this is what we're looking with. On top is the number of options he has. He's got 8. And on bottom of a permutation is the number of things he does not choose. How many blueprints, how many house models does he not choose? 3. So my denominator is going to be 3 factorial. If you want to write down 8 minus 5 and then move it to 3, do that. But I'm going to jump to it on this one, okay? So this one actually would not be terrible for us to just write 8 down to 1 on top and 3 down to 1 on bottom. But again, I'm going to model, if it had been bigger numbers, how I would do it. I'm going to write 8, 7, 6, 5, 4, and I'm going to stop at the 3 factorial because it matches the 3 factorial on bottom. Okay, all good? This part should feel familiar. The 3 factorials cancel. And then somebody's going to grab a calculator and multiply 87654 out for us.
Is it 6720?
That's what I have too. 6,720 ways that he could arrange 5 blueprinted houses, right? 5 model homes on 5 of these different lots from the 8 models he has to pick from. Okay, how are we feeling? Okay so far? Yes.
Where did you get the 3 from?
The 3, I actually got, there's a couple of ways you can do it. The way that I did it out loud was I said that the denominator is how many he doesn't pick. If he's picking 5, he had 8 to pick from, there's 3 he didn't pick. If you want to do it more like from a formulaic perspective, the denominator is actually n minus r, which is the first number minus the last number. So it's the 8 minus 5 showing up there. Yep. Okay, any other questions before we shift to the next one? Okay, this context should feel a little bit more familiar to you, although you don't have near as much flexibility as Julie has. Julie needs to take 10 electives to fulfill her hours in her degree. How many of you get that many? I don't think any of you probably do. In math education, I think our students get two electives the entire 4 years. They can add more, but they need to fill out the number of hours they have to have. Julie gets 10. That's exciting. 10 electives to fulfill her hours in her degree. She decides to start her career with electives because she is unsure of her major. We wouldn't do that either, right? We'd put you in comp and math, right? That's why you're here. There are certain things that we would put you in. But in her situation, this is the scenario they set up, so no judgment, right? We're just going to go with it. She gets to choose from among, so it says, if no courses have prerequisites of one another, and there are 17 courses she is interested in taking, how many different selections of 10 electives could Julie make? Okay, so first, just context is a little more familiar than the last context for most of us probably. If we're just looking at the context, we can make a decision about it being a combination or a permutation. So let's try this again. Let's see where we are. How many of you lean toward it being a permutation like we did the last one? Anyone think that might be the route to go? Okay. How many of you are leaning toward it being a combination? Okay. But are you leaning toward it being a combination because the last one was a permutation and you know I'm going to give you an example of both? No? I got some nods. Some of you are like, yeah, obviously it's going to be something different. So why do we think from context here that this might be a combination? Not from language, but context. David, what do you think?
Well, it's kind of like, for the way I look at it, is a mixture of the language and the context.
Okay.
It means to select, like choose 10 selections out of 17 options.
Yep. So selections is a key word there for sure. Selections tells us that we're looking at a combination. The other thing from context here that should tell you that is it talks about nothing needing prerequisites, which means the order doesn't matter, right? She can take them in whatever order she wants. So from the context as well, that pushes us toward the combination kind of approach. So it is a combination. She has 17 classes she can choose from, or ones she's interested in choosing from, and she's going to pick 10 of them, is what it said. Okay, pretty good so far. Numbers got a little bit bigger on this one than the last one, so our answer is probably going to have a slightly larger value at the end as well. So we have the number of choices on top always. That's 17 factorial. And then when we're doing a combination, we have two pieces in the denominator. One piece is how many she's going to choose, and the other piece is how many she's not going to choose. So let's start with the not going to choose just because the formula itself puts that first. There's 7 classes that she will not be taking. And there are 10 classes that she will. So the denominator has both the number of choices she makes and the number of choices she chooses not to make, right? Things she doesn't choose. Okay, that makes good sense so far. Yes, Jeremiah?
You subtract 7 from 10.
Mm-hmm. Yep, 17 minus 10 would give you the 7, right? The number that she does not pick, or the classes she does not take. So on the top, I'm going to write my 17 down to 10 because that's my first place I can stop with the denominator. And I will stop there because, I don't have to write as much. Look at that. It moved over today. It didn't try and copy paste anything. It's a good day. Okay, and then I have a 10 factorial on bottom. And then the rest of it, I need to write out. So 7, 6, 5, 4, 3, 2, and 1. You could choose not to write the 1 if you want to. I got the 10 factorials going away. Now again, if you wanted to, this is probably still small enough that you could multiply everything out on top, multiply everything on bottom, and divide. Pretty soon it's not going to be small enough, okay? We're really close to it not working out. So if it weren't small enough, that is, if you put this in the numerator and it puts it into scientific notation in your calculator, which is what will happen if it gets too big, what it means is you're going to have to go back here and you're going to have to look at some cancellations. So we're going to go from that perspective. And I'm just going to go from the 7 at the beginning. So the 7 at the beginning and the 2 here at the end make 14, right? And I have a 14 on top. So that's the one I'm going to choose to pair together to mark out with my 14. There may not be any others. There is one more. There's one more pair I could combine. I've got a couple choices. What are 2 other numbers I could combine together to cancel something completely on top?
3 and 5.
Okay.
15.
3 and 5 would be 15. Some of you might have said 4 and 3, which would have been 12. That'd be okay too. Is everybody good so far? Okay. Again, at this point, if you just wanted to multiply what remains on top, multiply what remains on bottom, it probably will work just fine. You could do that, but they will simplify further. What will this 6 simplify with? The 12. So this 6 will divide out with the 12, which will leave me with a 2. I have a 4 here. The 4 will actually simplify with the 16 and give me a 4. So looking at what remains, we have to be careful. You're going to have to write neatly, even if it's not in your nature to do so. Don't lose any of your values. 17 and 4, 13 and 2 and 11. Those are the pieces that remain. And what do you get if you multiply all of those together? 19,448. And I'll write selections, or you could write ways or something like that. This is how many different options she could choose. That's a lot. Right? That's a lot of different ways that she could choose 10 courses from 17. Okay. The next question that we're going to have is actually going to encompass all of the last pieces, I think. Yes, all the last pieces of information. So let me kind of preface a couple of things. Sometimes I get students a little grumpy at me for doing this particular example. Number one, because it feels like I'm overemphasizing this one thing. The reason I choose this example is because I can ask a lot of questions. We can move more quickly instead of having to do context every single time. The second thing is that I want you to understand is that I'm looking at a 5-card hand of cards. We're going to talk about the hands of cards we start with. And some of the stuff in my math lab does hands of cards, and they don't look at a 5-card hand. They'll look at a 6-card hand or a 4-card hand. So just because we're doing a 5-card hand here does not mean that you couldn't do this with something else, okay? So pay attention to the language that's being used in problems to see those nuances that are happening, all right? Okay, everybody good so far? Awesome. So if you don't know some of the details that I'm telling you, you need to write them down, or you're going to need to look them up later, okay? So depending on your exposure to decks of cards, playing games, will depend on your reference point on this. So I'm going to give you the information that you need in order to be able to do these problems. If you don't already know them, write them down. So first thing is, there are 52 cards in a deck of cards. 52, okay? Half of them, which would be 26, are red, and half of them are black. Okay, everybody good so far? Okay. There are 4 suits of cards. There's hearts and diamonds, and those are the red ones. So there's 13 the hearts and 13 diamonds. And then there's spades and clubs, and those are the black cards. So 13 spades, 13 clubs. Every card is unique. It has a color and a suit, right? It's the spade. And it has a number value or a value on it. The cards themselves, values, have numbers or they have some other things. Let's look at the numbers first. The numbers on our cards range from a 2 to a 10. So there's a 2, 3, 4, 5, 6, 7, 8, 9, and 10. There are 9 number cards from 2 to 10. Okay? But there's also other types of cards. There's a jack, a queen, and a king. And there's an ace. Jacks, kings, and queens are all considered face cards. Ace is not considered a face card, but neither is it considered a number card. So this is one of those things where it's not like there's number cards and there's face cards. We can't satisfy it like that. We can say number cards and non-number cards. We can categorize it that way if you want to put it into sort of a 2-category thing. But an ace is neither a number card nor a face card. And depending on types of games you play, ace can be high or low. And in fact, in some games, it can change in the middle of the game. If you've played blackjack before, that's one where the ace can take on either of those values, a high card or a low card, okay? So we're not going to talk about specific games, but I just want you to understand that there is sort of an ordering of these cards in terms of what's considered more valuable in most games. And it depends on the game as to what that looks like. So we're going to look at a number of different arrangements of things that can happen when we're looking at a deck of cards. So the reason decks of cards are so good for creating games is because of what we're going to find out on part A. The first thing we're going to look at is just simply how many different hands of cards are there in a standard deck. Okay, that's our first question. Before we do so, I want you to think about what happens when you play any card game. And it doesn't matter what card game you're thinking of. Actually, I don't think any card game I can think of that matters. So whether you're thinking of a poker hand, like what we're going to be looking at, or whether you're thinking of Old Maid or Phase 10 or Go Fish, none of those games, and you can continue adding on if you wish, actually matter what happens in the way that you are handed your cards. In fact, the first thing you probably do, depending on the game you're playing, is that you rearrange the cards that you were handed. Are you with me? Right? So if you're playing Old Maid, you're trying to hide the maid in the hand of cards. If you're playing Go Fish, you're trying to organize and put things together in these groups. If you're playing Phase 10, you might be doing something where you're putting numbers in order, or putting them with suits, or putting them with the number cards themselves. Lots of different orderings. But the first thing you do is that you take your cards and you put them in some kind of order. Right? Okay. So because of that, are we working with a combination or a permutation? It is a combination because the order of the cards doesn't matter, right? That is to say, the order they were given to you doesn't matter. So everything that we do in this next example, all the parts of them are going to be combinations, and we don't need to revisit that question because it's all dealing with a hand of cards. Everybody good so far? Fabulous. So first thing we're going to look at is just how many hands of cards are there. So to start with, how many cards did I say there were? 52. There are 52 cards. We said it is a combination. And how many cards are in this particular example's hand of cards? 5. So this is 52, C5. That number 52 is going to be large enough that we are not going to be able to just multiply the top, multiply the bottom, and divide. Your calculator will not tolerate that. Okay, we are beyond the point of being able to do that as an option. Now, top is going to be the number of selections we have. We have 52 cards that we could be handed, any one of the 52. And the denominator is going to be the number that we don't get. If we get 5, how many do we not get? 47. And again, if you want to write the denominator as 52 minus 5 to get to the 47 so that you can see that happen, do that. But 47 is the number of cards we do not get. Okay? And then the other piece is how many we do get. We get 5. Okay, combinations have 2 pieces in the denominator. The number we are choosing, the number we are not choosing, or the number we are dealt, in this case, the number we are not dealt. So I'm going to write this numerator out until we get to 47, right? And let me see if I can shift this down because I'll have more space if I do. So we're going to do 52, 51, 50, 49, 48, and 47 factorial. There's a 47 factorial on bottom, and then I have 5, 4, 3, 2, and 1. Okay, everybody good so far? All okay? Fabulous. The 47 factorials cancel. And this numerator is actually quite a large number. And if you put in your calculator, it'll turn into scientific notation. So we really do need to simplify pieces of the denominator to eliminate them before we multiply this together. Now, we can do some pairings if you want. You can do things one at a time as you want. The numbers on top are considerably larger than the numbers on bottom, and that hasn't happened in our examples so far. So it might simply be easier to just go from the largest one down and cancel some things out. For example, the 5 will divide what on top? 50. So I can mark my 5 out, I divide my 50, I get a 10. Which one do you want to use with 4? 48. So if I do 48 divided by 4, what do I have? 12. Okay. Which one do you use for the 3? You got choices.
52.
The 52 won't work. The 51 would.
49.
The 49 won't work. The 12 would. Let's do the 51 just for fun, okay? And you can use your calculator to see, right? We need something on top to cancel with a 3. Yep, it's 17. So if I notice the 3 goes into the 51, it will go in 17 times. If you want to put it into the 12, put it in the 12. It's fine. How about the 2? You got choices. 2 with the 12. Somebody said the 12. Yeah. So if you put the 2 into the 12, you'll get a 6 left. If you put the 2 into the 52, you're going to get a 26. If you want to put the 2 in the 10, you're going to have 5. Whatever. It's not going to matter. Just pick one that works. What's left? Well, we have 52, 17, 10, 49, and 6. And we're all going to be really careful in how we write them so that we don't lose any of them, right? Absolutely. Okay, if we multiply this out, how many hands, 5-card hands, can be created from a 52-card deck of cards?
2,598,960.
Yep. And this is why that simple 52 deck, 52 card deck works really well for games. That's a lot of variety. That's a lot of variety. You're never going to get the same hand twice. It's not going to happen. Right? You have a 1 out of 2.5 million chance of that happening. Not going to happen. Okay? So we can have games that are arbitrary and have some variety to them by having this many different options. What we're going to do next is we're going to limit what can happen and look at the different kinds of hands we could be dealt. The first one says, well, what if you want the hand to have all red cards? How likely is that to happen, right? Well, it's more likely than just general, right? It's going to be less than 2,598,000. It's going to be less than that, but let's figure it out. So we've got how many red cards? 26. And how many cards are going to be in our hand? Still going to be 5. 52 is what's in the deck, but 5 is going to be dealt in our hand. Okay? So we have 26 cards that could be dealt to us. If I'm going to get a hand that's all red, 26 is the number of them that could go in my hand. Yes, sir.
So since there's half and half, red
Mhm.
and black, and that's all, could you just just divide that by 2?
Okay, so Stone's got a really good question. Couldn't we take 2,508,960 and divide it by 2 to find the number of all red card hands? Think so? What do you think, David?
I think not, because that's counting all the cards, including the base cards.
Okay, so I don't think it's the face cards that creates the problem, but I do think there's a problem with just dividing it by 2. So let's actually answer your question first, Stone, by doing it and seeing what happens, and then we'll explain why that's happening. Is that all right?
Yes.
Okay, so we have 26 cards to pick from. So 26 factorial goes on top. How many cards from the 26 are not going to be chosen? 21. 21 of them are not chosen. And how many of them are? 5. Okay, so on top we have 26, 25, 24, 23, 22, 21 factorial. And on bottom, we have a 21 factorial, and then 5, 4, 3, 2, and 1. Okay, all good so far? Fabulous. So 21 factorials cancel, and let's do the same thing we did before. Let's start with the 5. What will this 5 reduce with? 5 and 25, leaving me with a 5 up here. How about the 4?
24.
Okay, 4 and 24. 6, actually, on that one. Yeah, so we'll leave with 6. And you can do the 3 and the 2 separately, but I actually happen to notice something happens here that's kind of fun. 3 times 2 actually is 6, and that's the 6 that we just got out of our 24. So if you notice that, you could cancel that too. So what do we have left? Well, we have a 26 and a 5 and a 23 and a 22. So what do we get when we multiply 26 times 5 times 23 times 22? 65,780 hands. Okay, so let's revisit Stone's question. Stone, is it half? It's not half. In fact, it's considerably less than half, isn't it? Why? Why is it not half?
Just the combination more than doubles because of the different ways that you can combine all the cards.
Okay, you're right, Jonathan. Can you give me an example of what you're thinking?
Well, like, I can get 5, so then I can get, like, if I have 26, right, 26 black, we're swinging a third, like 2 2s in one hand and 2 in another,
Okay.
right? So I can go from having only 2 2s as an option to 4 2s, plus that one other card, all the different.
Okay, let me piggyback off of what you're saying, but slightly change your language because you're on the right track. If we were just to divide by 2, which sort of feels like it should be right, and it does, right? Half of them. What we would be saying is that there's going to be only hands that are all black and only hands that are all red. But what you're saying, Jonathan, is that I could have, for example, all 4 2s in my hand. And if I did, that would mean my hand has some that are black and some that are red, right? Right, there's an excluded piece if we say it's all red or all black. What about the hands that have both? And that's why we can't divide by 2, is because some hands are going to have both as well. In fact, most hands are.
So if it was like hands of all black and hands of all red, then it would be.
Sure, if those are the only 2
I see.
possibilities, it could be, yeah.
Okay.
Yes, Jeremiah?
Do you cancel 3 and 2 in that, or is it included?
I canceled the 3 and the 2 with the 6 on top. I didn't mark them. Maybe that would be helpful. Yeah, I did cancel my 3 and my 2. I always cancel everything in the denominator before I multiply. Okay, does that make sense so far? We're going to narrow our focus just a little bit because I will tell you that if you were playing poker, nobody cares if you get all red cards. It's way less common, but nobody cares. Okay, it's not a very, like exciting hand. There's still 65,000 ways it could happen, right? That's not real rare. But what happens if you have a hand that's all hearts? That actually has a name. Does anybody know what a hand of all hearts is in poker? It's a flush. Okay? And if you don't know that, it doesn't matter, but it is. It's got a name. It's rare enough that it actually matters. So let's actually figure out what happens when we want to have a hand of all hearts. So how many hearts are there? There's 13. And how many cards are in my hand? 5. It's going to be 5 every time. We're doing a 5-card hand. So on top, I have 13 factorial. On bottom, I have the number I don't choose, which would be 8, and the number I do choose or get dealt, which is 5. Okay, if there's 13 cards that are hearts, I get 5 of them, 8 more of them are somewhere else. And we'll write this out. 13, 12, 11, 10, 9, 8 factorial over that same 8 factorial, and then 5, 4, 3, 2, and 1. Okay, the 8 factorials cancel. Fantastic. There's actually a couple of pairings that work really nicely with this one. Do you see anything on bottom that pairs up nicely on top? 5 and 2 actually make 10. So we could actually cancel the 5 and the 2 on bottom with the 10. And what else? Yep, the 4 and the 3 actually pair up really nicely to cancel with the 12. So I end up getting 13, 11, and 9. How many how many hands that are all hearts, so heart flushes, do I have?
1,287.
Yep, 1,287. Now, that's a lot, but it is nowhere near 2,598,960, right? Very significant jump downward. It is uncommon. It's rare. And so if people are playing poker, my husband used to watch a poker channel when we were living in Ohio. He hasn't watched it in forever. He watches other things now. But they would write down like the percentage, how likely certain hands were in the bottom of the corner of the screen. And they're doing this math. I mean, like the computer is doing it, I get that. But that's what's happening is they're looking at these rare situations and whether or not that hand is a rare hand or whether it's going to be a normal hand. And he actually watched Texas Hold'em is what he mostly watched. But, okay, so we have hands of all hearts. What about hands of all jacks? Zero.
Impossible.
Why?
Because there's only 4 jacks to get the cards and there's 5 cards in hand, so it's impossible to handle all jacks.
Okay, so I'm going to say it a little louder too, just to make sure everybody got that. How many jacks are there? There are 4 jacks, 1 of every suit. And how many cards are supposed to be in my hand? 5. So I cannot have a hand of all jacks unless I'm cheating. Agreed? Or unless you're running more than 1 deck of cards, which you could then, right? And that would be some games as well. That's not the game we're playing here. But there's no hand that has all jacks. So there are 0 ways that this can happen. I don't need to calculate anything. So before you start calculating, look at what the question asks and make sure that it really makes sense before you move forward. Now, the next one actually does change that. It says I have 4 jacks and something else, right? So I'm actually going to show you a couple of ways to write this out. The first one being the more general form. So we have, as y'all mentioned, 4 jacks. And I need to pick all 4 of them. 4C4. Right? There's 4 jacks to pick from. I need to have all 4 of them. But that only gets me 4 cards. I need 1 more. So this actually pushes you back into the fundamental principle of counting. This gets me 4 cards. I need 1 more card. How many more cards are there besides my 4 jacks? Okay, there were starting with 52, so now there are 48. 48 cards left, and I need to pick one of them. So this is a general way. It's going to lead nicely into F when we get here in a second. Let's calculate it, and then I'm going to actually show you there would have been an easier way to do this particular one with these details. So 4C4 means I have 4 factorial on top. There are 0 cards I don't pick and 4 cards I do pick. And then I have 48 cards on the second piece. There are 47 cards I don't pick and 1 card I do pick. This is what this would actually be coming from that notation. Do you guys remember what 0 factorial is? It's 1. Don't be led astray. When 0 factorial shows up, it's the number 1. So in this first piece, when I have 4 factorial over 0 factorial, 4 factorial, what do I get? I get the number 1 here, right? This is equal to the number 1, and these cancel. I get 1. And then on bottom, 48 factorial over 47 factorial. If you think about what this looks like writing it out, it's 48 times 47 factorial, like that. And you got a 1. And the 47s cancel, which leaves me just with 48. So there are actually only 48 hands that have 4 jacks. That's very uncommon, correct? 1287 was very uncommon, but this is even more so. True? By a lot, actually. Yes, sir?
So is the shortcut kind of just since there's the 4 cards that have to be in it, just assume that the other options for that 1 card that make up the answer are just the rest of the cards?
Yep. So you're exactly right. The shortcut is to recognize there's only one way to get all the cards that do this, because it's all of them, right? Because the order that they give them to you doesn't matter. So there's one way that this happens. You simply get all of them. And this one is getting any other of the 48 that's left over. This can be interpreted just as a fundamental principle of counting directly like that. Now let's take a look at what happens though when it's not 4 of a kind, but full house. Does anybody know what a full house is? Not 4 of a kind, but close.
3 of one, 2.
3 of one and 2 of another. It's a full house. So another game that shows up in is Yahtzee, which is a dice game. There's full houses in Yahtzee. So full house means you have 3 of one number card, value card. I should say value card because it could be jacks, kings, queens, or aces. And then you have 2 of some other value card. Okay, everybody good? Okay, so the way that this works is we first need to pick what, I'm sorry, this is 4 of a kind. I was jumping to the next one. Let me do 4 of a kind first, which is why somebody said we're looking at 4 of a kind. I was doing our next one. Look, full house, this is what I was moving to. Let me jump back to 4 of a kind. Okay, we know that there are 48 all jack hands, correct? But that means that there's 48 all 10 hands, and there's 48 all 7 hands, and there's 48, not all, but 4 of a kind, right? There's 48 of them that have all 10s and 12s, and not 12s, 10s and 6s and 4s and 5s, and there's 48 of each of them, right? Are you with me? So I could literally, one way of doing this is say, well, okay, there's 48 that have 4 2s, and there's 48 that have 4 3s, and there's 48 that have 4 4s, and there's 48 that have 4 5s. And we could do that all the way till we get to the ace. And we could add the 48 together all that number of times, but is there a shorter way to do that? 48 times, nope, 48 times something, but it's not 48. 13. It's not 13 factorial though, it's just 13. Okay, so how many different how many different value cards are there? There's 13, right? There's 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. There's 13 different values that the card can hold, right? So there are 13 different ones of these. And if I were doing that, adding things together, I would have added the number 48 together 13 times. Well, repeated addition is the same as multiplication. So I could take the 13 and simply multiply it by the 48 instead. And 13 times 48 gives me 624 hands. So getting 4 of a kind, any 4 of a kind, is rare. 624. And if I got 4 of a kind, And if Jordan got a flush over here, which is what we are, the hands that are all hearts, right? Mine would be more rare than yours, right? Because you actually have 1,287 that are all hearts, 1,287 that are all diamonds, 1,287 that are all clubs, and 1,287 that are all spades, what I have left, spades. So there's like almost 5,000 or thereabouts. There's about 5,000 of those hands. It's 5,000 hands that would be a flush. But there's only 624 hands that would be 4 of a kind. It's more rare. This is how they make determinations in games like this about who wins. What's more rare? What's more uncommon? This one's more uncommon. Sorry then, let's do the full house that I was trying to get to before. Full house, 3 of one, 2 of another. Okay? So how many different choices of value cards are there? We just did this. 13. There are 13 different value cards, right? If I need to get, once I pick one, because there's 13 of them that could have been chosen, right? There are 13 different choices of a value card. Once I pick one, for the sake of the discussion, let's just say it's a 5. Okay, it's a 5. How many 5s are there?
4.
There are 4. And how many of them would I need if I'm working on a full house type hand?
3.
I need 3. There are 4 of them, I need 3. Once I have those 3 5s, let's say, I need another value card. How many value cards are there remaining? Not 13 times 4, not 9.
2.
How about 12? Think with me for a sec. I picked 5. That was the one I arbitrarily picked, right? So if I get 3 5s and I need another value card, I need some other value card that's not a 5, right? How many value cards are there left to pick from? 12. 2, 3, 4, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. It's everything but the 5s. I have 12 other choices available to me because I made one choice and there's 12 left. Are we tracking? Is that okay? So there's 12 different choices then that I could make for my second one of my options in my card of hands, my hand of cards, sorry. Let's say this time it's an ace. I've got a full house that I'm trying to fill out. How many aces are there? There are 4. How many aces do I need in order to finish out my full house hand? 2. Why do I need 2? Because I already had 3 5s. That's the chosen one I said, right? I already had 3 of one. I need 2 of whatever else I'm choosing. So this 13 and this 12 here are determining a value card. And then the C parts, the combination parts, are saying once I have that value card, I'm counting how many of them there are and how many of them I'm choosing. So let's finish this one out. We have 13. I have 4 factorial on top. I don't choose 1, I do choose 3. And then I have 4 factorial on top. I don't choose 2, and I do choose 2. Okay, so admittedly, 1 factorial is very unexciting. We don't really care much about it, right? It's just the number 1. On the top of this second one, though, the second piece here is 4 times 3 factorial. So it will cancel with the 3 factorial on top, or on bottom, rather. The top and the bottom will cancel like that. I still have a 12. And then I have 4, 3, 2. If you want, you can write the 1. And on bottom, I have 2, 1, 2, 1. So what over here is going to cancel?
2 times 2.
Yeah, the 2 times 2 is 4 here. This 2 times 2 is 4. Or you could cancel one of the 2's with the 2 on top, and then the other 2 with the 4 would be fine as well. So what do I end up with? Well, I end up with 13 times 4 times 12 times 3 times 2 times 1. What does that give us? Yep, that's what I have. 3,744 hands. So a full house is less common than getting 4 hearts. That was what we did before. But it would be, I'm sorry, not 4, 5, but it would be more common than getting 4 of any suit, right? Because I would have 1287 of hearts, 1287 of diamonds, 1287 spades, 1287 clubs. So this full house hand is less common than a flush. Okay? I'm throwing this out there because I want you to give some sort of sense of why people care. But the calculations is the important part in terms of what we're doing, okay? We go with that? All right, let's just do one that's random. There's absolutely nothing special about this hand of cards, and you will see when we get to our answer why. We are going to consider a 5-card poker hand. We're going to find how many would have 2 black cards, 2 diamonds, and a heart. It's a random assortment to get our mind back into the idea of counting what's remaining, okay? So, starting with black. How many black cards are there? 26. And how many am I supposed to be selecting? 2. That's 2 of my cards. The next 2 are supposed to be diamonds. How many diamonds are there? 13 diamonds. And how many am I selecting? 2. The next one is hearts. How many hearts are there? 13. And how many am I selecting? 1. Okay, does everybody see where each of these pieces came from when we wrote them down on counting things up? Okay, we're going to put them back into those formulas we've been working with now. So we've got 26 factorial on top. How many am I not picking? Well, 24. How many am I picking? 2. The next one I'm picking from, there's choosing from 13, so 13 factorial on top. How many am I not picking? 11. How many am I picking? 2. The next one, there's 13 hearts, so 13 factorial on top. How many am I not picking? 12. How many am I picking? 1. Okay, how are we doing? Doing okay? All right, so we're looking at this 26 then. So I'm going to write 26 times 25 times 24 factorial, which marks out with the 24 factorial on bottom in a moment. And I have 2 times 1. 13 times 12 times 11 factorial to cancel with the 11 factorial on bottom, and then I have a 2 times 1. And I have a 13 and I have a 12 factorial stopping to cancel with the 12 factorial on bottom, and then I have a 1. Okay then, 24's gone. What will the 2 simplify with? 26, and 26 divided by 2 is 13. Okay, 11 factorials, gone. And the 2 will simplify with the 12 to give me 6. And then the 12 factorials gone. I don't really have to worry about the one on bottom. I've just got that 13 on top. So I have 13, 25, 13, 6, and 13. Lots of lucky 13s. Okay, what do I get when I multiply this together?
329,500.
Okay, I think that's what I heard. 329,550 hands. Sorry, my numbers all kind of crunched together, but it's very common, right? There's 300,000 of these guys. So nobody cares if this is what your hand is, right? Because there's lots of hands that are going to be like that. It's very common.